time and clocks in distributed systems. In this lecture, we will introduce the notion of physical time in distributed systems. By doing so, we will be able to implement abstractions that we are not able to implement in the pure asynchronous system model. And we can implement some abstractions more efficiently. In particular, we are going to describe a lease-based leader election abstraction and its algorithm, where different leaders are guaranteed to have disjoint time periods. Second, we will introduce interval clocks, where all processes in the system are guaranteed to have overlapping time periods. We then use interval clocks to implement a linearizable shared memory where both read and write operation take only one round trip or 2 messages to complete. So let us start. We will start by motivating the use of physical clocks. And we will do this in 2 algorithms later. One is a time-based leader lease algorithm, and the other is shared memory using physical clocks. So this is the schema of this lecture. So we start with some motivation. So we are going now to consider a slightly stronger system model. When it comes to computation, there are no bound on the time it takes to make a computation step. So processes can take arbitrary time to complete any step in their computation. And we still have asynchronous system when it comes to communication, so no bound on communication delays. So far, this is the asynchronous system model that we have been describing. But now we introduce a little extra concept, which is we introduce physical clocks at each process. And what is the assumption about the physical clocks? Processes have physical clocks, but the lower and upper bounds on the clock rate is defined, which would mean how many ticks a clock can do in 1 second is well defined and stays within an upper and lower bound. So this is our assumption, and actually clocks in most of the current processors have this specification. And in fact, this is then a fairly weak model. So what we have done here is just we introduce these bounds on clock rates. And just to support our claim that we can build algorithm using this, we can look to what engineers at Google say. Our machine statistics show that bad CPUs are 6 times more likely than bad clocks. That is, clock issues are extremely infrequent relative to much more serious hardware problem. So this assumption is practical for all practical purposes and for all practical systems. So why do we consider algorithms that use clocks? By making stronger assumptions about the system, we can get better efficiency and performance. In this slightly stronger model, we cannot still solve problems that are harder than that we can solve in the asynchronous system model. For example, the impossibility of consensus in the asynchronous system still holds. But we can define some abstraction with better properties, as we will see now in the lease-based leader election. So let us now introduce the time-based leader leases. And this unit will be about motivation for time-based leader leases in replicated state machine or in other applications. We will do this by the following. We will, in the first unit, discuss the optimization opportunity by using leader leases. What can we do, which we cannot do before? Second, we are going to show the proposed algorithm, and we are going to argue about the correctness of this algorithm. Let us assume that we are implementing a key value store using replicated state machines. This means that you take the key value store and you divide the key space, and for disjoint key spaces, you implement each disjoint key space by a replicated state machine. This replicated state machine supports the following commands. What are the commands? It supports read the value given a key, write a value for that key, and perform compare and swap operation. Now, compare and swap is an atomic operation that cannot be implemented in the asynchronous model by just the previous algorithm that we described, the algorithm of shared memory in the chapter of shared memory, or the section of shared memory. So let us just understand what is compare and swap. To compare and swap, we have a key and we write a new value associated with this key if this is the old value of v expected is the old value. And in any case, we return the old value. This is an atomic operation because compare and swap has to read the value written and see if it is the old value or not, or it is the expected value, and atomically rewrite this value if that corresponds to the expected value that we have here. So we need a replicated state machine to implement compare and swap because the shared memory model that we described before is too weak. Remember that the shared memory model in the asynchronous system allow for atomic read and write registers, but not any stronger type of operation. And for that we need consensus, and that's what we implemented with sequence Paxos or Raft or other replicated state machine that we discussed before. The service runs a leader-based sequence Paxos. Assume we have 3 processes, and so we have 3 replicas, P1, P2, and P3, and we run a leader-based sequence Paxos, and each replica could be a proposer, acceptor, or a learner, and when it becomes a leader, it becomes the proposer, as we just discussed before. So the sequence Paxos or the replicated state machine guarantees that all replicas execute command in the same order. So here is an example. If you start with the empty state, you do a write operation, then you have the state now x equal 1 because you are trying on the variable x write the value 1. And if we start from x equal 1 and we do write y equal 0, we get this state. And these operations are executed sequentially one after each other. So if we read x here, we will return the value 1. This did not change the state. The state here is the same as the state of the next operation. And here we come to a compare and swap operation. Compare and swap says that if the old value is 0, I can update it atomically to the value 1 and return the old value. So here the old value is returned, and now y has the value 1. And so on. Here's another operation of compare and swap. And this compare and swap does not have an effect, does not change the state, because the old value now is not 0 anymore, and so on. So this is the execution of one state machine, and all replicas in the replicated state machine execute these operations in the same order, like this. So now let us see what happens when we have clients and leader-based replicated state machine. We have our set of replicated state machines here implemented by P1 to P3, 3 processes, and the other processes in blue are the clients right now. So we assume the network is stable and P1 is a leader. And P1 is a leader, and so it has started a new round. So let us see what happens when a client tries to execute a command. If client P4 wants to execute a command, so it sends a request. This is a request to the leader. This is one step. What happens then? When the leader gets the request, it extends its sequence, it performs an accept. So it sends an accept to itself and to the 2 other replicas. That is fine. So that's an accept message. And then what happens is that it gets back an acknowledgement. And when it gets back an acknowledgement from a majority, say from P2 and itself, then it can now decide and execute the operation. Fine. So after P1 gets the accepted or accept messages from a majority, the command order is known, and P1 sends a decide and the replicated state machine now can execute the operation sent by P4. So at this stage also, P1 executes the command, and this command could be any command using the state of the local state machine, and it sends a response to this operation to the client P4. So let us see now the sequence of communication that led to the execution of this command. We started with P4. P4 sent a message, P1, this is number 1. P1 sent a message to its replicas, and it sent maybe to itself, P1 and P2. And it got an acknowledgement for the accept. So P1 got an acknowledgement for accept. So we have 1 message, 2 messages, 3 messages. And once it got an acknowledgement for the accept, it can now decide, and it can also at the same time send a message back to P4. This is called P4 prime. So it took 4 steps for the request from the client to complete the operation at the replicated state machine. So now let us assume we have some operation that we will ask ourselves, can we do these operations faster than that? Before we had 4 steps. So one way to think of is that if the operation is a read operation or any other operation that does not change the state of the replicated state machine, why not make the leader respond immediately? He has anyway the updated state, so he has the information to respond immediately. So assume now the operation requested by P4 is a read operation. And because P1 stores the entire state, P1 can read the state variable X and respond immediately. So here's a situation where P4 send a message 1 to P1, and P1 send back a response to P4. 2 communication steps. That is great. The question is this is correct? Can we do that? Can we let the leader immediately respond to our client on operations that do not change the state of the replicated state machine? That is what we are going to discuss now. In fact, it will not be possible. And here we're going to show you what can go wrong. So assume now a network split or a partition which partitions P1 away from P2 and P3. So here is the situation. P1 is in its own partition, and P2 and P3 are in their own partition. And now, after this partition, we assume that P2 is elected a leader, and that is possible because there is a majority here, so P2 is elected a leader, but P1 never hears about that. P1 does not know, he thinks he's still a leader, and because he is not getting any messages across partitions, so he still thinks he is the leader. Now, assume a client, which in this case P9, performs a write on the variable X. This is the new value to be written. It's a request coming to P2. So here is a request. P9 send a request to P2. This is first step. And P2 communicates with P3. It is this way. It is this step. P3 communicates back. It's fine. And now P2 responds to P9 in this message going this direction. So what we see here is that the state of the replicated state machine for the variable X has changed to a new value. So assume after that P1 gets a read request from P4. So P1 gets a read request from P4, and in this case P1 is unaware of the split and is unaware of the write operation. So P1 responds to P4 with the old value of X. So now we have a situation where the replicated state machine has updated its value, but P1 is responding to the client P4 with an old value. This is a violation in the strong linearizable consistency because the read operation should be ordered after the write, but it has returned the old value. This is fine in weaker models such as sequential consistency, because in sequential consistency all state updates are still ordered and reading all values is allowed as long as process order is still satisfied. But for strong consistency, linearizability, this is not allowed. So here is our situation. The reason process P1 cannot respond with its current state because some other replica may have assumed leadership and modify the state without the knowledge of P1. This is the reason. So P1 is not allowed to do that. The question is there some way to avoid this? One possible approach is the following, is to let P2 communicate with P1 before P2 can become a leader. But this will not work. The reason for that is P2 cannot communicate with P1 because, first of all, because of network partition, or because P1 might be dead. So this is not solvable. This is not a problem that we can solve this way. So the solution is to develop a leader election abstraction that guarantees that different leaders cannot overlap in time. This is not possible in the asynchronous system without introducing some notion of time. And that is what we are going to cover in the next unit.